and I will do a share screen. And yes, I've been writing on my iPad. So thanks for putting my attention to that. Somehow I missed that. All right, so from the start, right, since now it's being recorded. So first, thank you very much that you remind me in case I forget to record or to share my screen. So last time we've been, quick recap, we've been discussing curvature, right? And we started by defining the concept of a parallel transport, which is transporting a vector along a path or a curve in a way which makes it parallel to itself, unlike the plot that I draw here. It doesn't look very much like parallel to itself. It should look more like that. Right, and mathematically, when we say parallel to itself, meaning, you know, it is not changing. So the V over the lambda, or the V, or I should say dV over the lambda, which is dV over dx mu over the lambda is equal to 0. Right, so we want to do the same in a curved space-time, right? We choose a path lambda, and we take a vector, and we just transport it parallel to itself. And of course, what will happen now is that we, instead of the partial derivative, we will write it in terms of covariant derivative. So that gives us d over the lambda, which is just dx mu over the lambda mu. This is the concept of a parallel derivative, right? This is the concept of a parallel transport. And the advantage, of course, is that we can generalize that immediately to any tensor of any kind, any rank. It doesn't have to be a vector, right? And this gives us the equation of parallel transport, d over the lambda of tensor t, let's say mu nu, is just the regular derivative dt mu over the lambda plus a fine connection gamma mu sigma rho dx sigma over the lambda t rho nu, and then will be a minus for the lower index gamma rho sigma nu dx sigma over the lambda t mu rho. And that's true for any tensor of any rank. This is the equation of parallel transport. And then we define the curvature by basically taking a vector and parallel transporting it from point 1 to an infinitesimally closed point, you know, from A to B, right, along two different paths and looking at the difference, right? So we had first point A, second point B. We call this a 0, 0. And the paths that we choose go along two vectors that we arbitrarily chose, right? A mu, which took us to some point infinitesimally far away, so delta A and 0, and then B nu, which took us to delta A, delta B. And then we choose the second path by first going along B nu, so 0, delta B, and then A nu, which get us back to the same point, but along a different path. And we saw that the change in a vector, so when we take a vector v, and we do this parallel transport along the first path and along the second path, right? We know that the change in the vector, right, should be, or let's use sigma because I already used mu, should be, you know, linearly proportional to v sigma. So delta v should be linearly proportional. So I call it delta v rho is proportionality Okay, it should be proportional to V, but also to the passes. So delta A, delta B. Why are you doing that? A mu, B mu, and then we have the tensor that would contract all these. So rho, sigma, mu. And it's obvious by the way we define it that it has to be anti-symmetric in the last two indices. So R rho sigma mu nu has to be a minus R rho sigma mu mu.
Asaf, can I stop you for a question?
Yes.
So we said that the curvature was asymptotically, well, I mean, it's flat when we're looking locally, right? When like the surface of the Earth. Locally it's flat, and but globally it's curved. So
Yeah.
how if we are going an infinitesimal path like you showed here, why would the vector change? Because it has to be locally flat, right?
Well, by locally flat, I mean that it is well behaved. Namely, you don't have any spikes or corners, right? But although the Earth, if you look at the full circle, right, an entire circle, right? Let's take even one two-dimensional have to take, right? If I zoom in, right, it will look more and more flat, right? But it will never be exactly flat unless you go to zero. If you go to zero, it's going to be exactly flat. But it's not really flat. That's the whole point of an infinitesimal thing, right? In some sense, it's like taking the derivative, right? You're taking a derivative, you're taking limits of things which are infinitesimally close to each other. So the difference is zero, but it's not really zero, right? And you see that the change in the vector can be zero only if delta A or delta B are zeros, right? Because the surface of the Earth, is asymptotically flat, right? If you zoom in and zoom in and zoom in, it's going to be closer and closer and closer to flatness, but it's never going to be exactly flat.
Right. So it looks like a fine line.
Yeah, think of it again. Think of a ball. You take a surface. It looks pretty much rounded, right? But you zoom in, it's flatter, right? You zoom in even further, it's even flatter. But it's never going to be exactly flat, right?
Right, I understand that, but I thought the locally flat meant that if I take a really small delta, it's like going to zero, like you said.
No, well, yes and no. I mean, that's the whole point of an infinitesimally, right? I guess you learned it in your calculus or Hedva or Infi, right? If you give me a number, right, which will describe how close to flat you want to be, I can give you another number which will tell you how far from the point you need to be in order to be as close to this flatness that you want. Right? For every delta you give me, I can give you an epsilon.
Right? Okay, thank you.
The surface of the Earth, if you zoom in and zoom in and zoom in a microscope, it looks very much flat, but it never is exactly flat. I mean, mathematically speaking. I'm not talking about mountains or anything, right? But mathematically speaking, it's going to be close to flat, but it's a sphere. It will stay a sphere, right? And regardless, whichever you go, right, if you're going close to a point, right, with this delta A and delta B, you're still never going to get flat unless you take delta A or delta B to be equal to zero, which of course you stay at the same point. The point of asymptotic flatness means that it is well behaved. You don't have any spikes. You don't have any corners, right? It is a round circle. It doesn't look, like that when you look close enough. Now you can ask, okay, what about quantum mechanics? And we're not going to do quantum gravity here, unless you really insist, but then we'll have to go through something else. Let's stick with that. Okay, we have classical surfaces. If you go closer and closer and closer infinitesimally, it's going to be as close to flatness as you want, but it's never going to be flat because the Earth, or the surface of a sphere. for a ball. All right?
Okay, thank you.
Okay, good. Okay, and then we actually derived the Riemann tensor by taking the commutator of two baryon derivatives, and we discovered that our new rho sigma actually looks like, or sorry, to be consistent with the way I wrote it, and not to get myself confused when the English says R rho sigma mu nu is d mu gamma rho mu sigma minus d mu gamma rho mu sigma plus gamma rho mu lambda gamma lambda mu sigma minus gamma rho mu lambda gamma lambda mu sigma. So we end up that the curvature tensor, or the other term is called the Riemann tensor, after Riemann, of course, we discovered it. Right. Is constructed from the affine connection, which by itself we constructed from taking the derivative of the metric and the inverse of the metric, and from the first derivative of the affine connection. So really, if we know the metric, right, we can take the first and second derivatives of the metric and we get the curvature tensor. So everything we need to know about the properties of the space are written in the metric, embedded in the metric. Right? Now, the last thing I did, but I did not completely do it because I told you it's a bit ugly. One way is simple, but the other way is not so simple, is to argue that a necessary and sufficient condition for the metric to be equivalent to a flat metric, Minkowski metric, right? Equivalent in the sense that it is always possible to find some transformation of coordinates from x to psi, is that the components of the curvature tensor vanish everywhere. And the second condition is that the metric has 3 positive and 1 negative eigenvalues. Right, let me just write it down. The necessary and sufficient condition for the metric x to be equivalent to the Minkowski metric in the sense that one can find a transformation from x to psi are 1, the components of the curvature tensor, all of them. There are plenty. How many? Two, the metric mu has 3 positive and 1 negative eigenvalues. Some noise there, somebody. I hope it's not me. All right. And this, by the way, helps you. Now we have a rigorous way of proving. If I'm giving you a metric, you can know if it's flat or not, even if you don't know if it does look, strange because I chose strangely looking coordinates. You have a fail-proof way, fail-safe way of proving whether the metric is equivalent to flat or not. But it's going to be quite long to do that because we have to calculate all the components of the Riemann tensor. How many components does the Riemann tensor has, by the way? You did not answer me.
4 by 4? Yes, 4 to the power of 4?
4 to the power of 4, right? So how many? How much is 4 to the power of 4? You don't need a calculator for that. Come on. You don't need a calculator for that.
256.
256, right? In 4 dimensions, right? But there are theories which contain more than 4 dimensions. Right. Okay, questions?
I have a question, but it's is there any sort of analogy for the fact that we use oh no, I forgot the operator. For the fact that we use a commutator here and the usage of commutator in quantum mechanics, or are they two completely different uses for the same mathematical object?
No, a commutator is a mathematical object. In quantum mechanics, it has a physical interpretation, right? You say that you have two observables, right? That some of the observables do commute and some of them do not commute. And that is important from the point of view of making an experiment, right? Because one of the foundations of quantum mechanics is that if you have a set of observers which commute, you can measure exactly the values of them. And if they do not commute, you cannot measure exactly. There is the hazard uncertainty principle. Eventually, it tells you. Now here, so far, we have not spoken about physics, about physics at all. We have just used the commutator as a mathematical tool of deriving the Riemann tensor. So far, we're not doing any physics, right? We're just building up some tools.
Yeah, I mean, does it not have anything to do with the Hilbert spaces that they occupy?
No. Hilbert spaces are something more abstract, right? Which you need to have in quantum mechanics because then you're quantizing your space essentially, right? So you're describing your physics, right? It's wave functions, and the wave functions can only get some discrete values. They cannot get any values that you want, right? That's why we call them they're a set of elements in an abstract space, which we call Hilbert space. But that goes out because we are quantizing things, right? Here so far throughout this course we're not going to quantize anything. Again, it's not a quantum gravity. We're doing basic classical gravity. Okay, there is a quantum gravity, and I won't get into that in this course. If you really want, you go to Yossi and ask him to do something more, advanced quantum mechanics. And then there are other things which we'll discuss.
Thank you.
So the answer is no. This is uses of the same mathematical operator to do something else. Any other questions? Okay, I have some comment for you before I proceed. So this was a recap on what we did. If you have any further questions. I had a little bit of trouble with the way somebody is supposed to grade your homework. Never mind, I don't need to get into the details. It might end up that I'm grading your homework. So I started to grade your homework. You might have seen that, most of you. Definitely trying to do that you won't get hurted by some problem she has. So a few comments. What I like is that some of you are clearly working independently, and I really like that. Some of you, I'm less sure that you completely work independently. I'm not going to get into that. If you work independently, there is, of course, a higher risk that you do something wrong. Don't get this discourage you. On the contrary, I am pointing out when you're doing something wrong and you're losing a few points, but it's really a minor point. You end up losing a few points. Remember, you know, if you lose 10 points in the one of the exercise, it's there will be of the order of 10 exercises in the semester, and the total sum of you know the exercises in your final grade is 20%. So you're not really losing anything. You're gaining comments, which are very useful, and you're gaining experience in working with that. And I may ask you to, you know, derive the geodesic equation in the exam. If you practice it at home, it will be easy. If you let somebody else do it for you, then you're going to lose a lot of points if you don't know how to do it in the exam. So, you know, spend your time now, do that. If you don't know, ask me. Some of you do ask me, and I do answer. You see that. One comment which I did see, gamma, right? The affine connection. It is not a tensor, and you cannot write it in the form of a matrix. Right? Forget about it. Tensors, you know, G mu nu, you can write as matrices. But gamma, you cannot write as matrices. Don't do it. Okay, it's a mistake. Other things, in exercise 3, there is nothing really major, but mainly in question 1, you actually had to show directly that what you get there is flat by doing some transformation. Some of you did the transformation, some of you did not. So if you did not, then you have to do it. Now, some of you made some typos in calculating the affine connection. That's great. That's what you're given the exercise for. I'm talking about exercise number 3. That's what the exercise was for. To practice calculating the affine connection. And if you made a typo, it's fine. Don't get too nervous. And it's technical, so it's fine as long as you know what you're doing. Try not to make typos in the exam. But again, you know, it's the kind of things that the more you practice, the less likely you make mistakes. Okay, more questions or issues before we start today's new topic? Okay, if not, I promised you that today we're going to have a little bit of more on the algebraic side. So don't get too nervous, because I want to derive some properties which will turn out to be quite useful and important for us in what's going to come. So what I'm going to do now, I'm going to do algebraic properties and to derive algebraic properties of the Riemann tensor. So, obviously, as we already discussed, when we speak about n-dimensional spaces, right, the Riemann tensor has n to the 4 components. And these spaces. Sometimes we just call the Riemann. You say Riemann, it's theoretical, it's a Riemann tensor. There's nothing else that was attached to the Riemann. Okay, but that does not mean that they are only dependent. In fact, we already saw that it is not all independent, because it is anti-symmetric in the last 2 indices. Right? So That means that as far as the last two indices, right, they're only anti-symmetric. So it has only, they have only n times n minus 1 over 2 independent values. Do you all see why? Just to be on the safe side, right? Let's say I have the last two indices, mu and nu, right? But they have to be, so there is n dimensions. So there is 1 to n. Let's say it's a 4, right? So they can have values, you know, all of that is filled with values, right? But they're anti-symmetric. So if I have mu nu and mu needs to be the opposite. So this means that these ones need to be 0. And that this guy here is exactly the opposite of this guy here, right? So the number of independent, or only these ones are independent. Right, and then dimensions, the number of independent components of the last two indices is just n times n minus 1 over 2. Yeah? You've seen that sometimes in the past. Okay, these are not the only symmetries of the Riemann tensor. In fact, it has plenty of symmetries. And we're going to derive them right now. But again, I told you that it's a bit annoying to derive. So we'll just go over them and hopefully not too many typos. So to derive additional symmetries, I'm going to take the Riemann tensor with all 4 indices low. So derive other symmetries. I'm going to define the Riemann tensor with all indices low, R rho sigma mu nu as simply G rho lambda R lambda sigma mu nu. Right, that's how I lower indices. And then I am just going to do that to use the definition of the Riemann tensor from here. Take it down and write it down as G rho lambda. So if I won't make mistakes, G rho lambda, D mu gamma lambda mu sigma minus D mu gamma lambda mu sigma plus G rho lambda gamma lambda mu alpha gamma alpha sigma mu minus gamma lambda mu alpha gamma alpha sigma mu. Okay, that's just plugging in the definition. So now I'm going to simply expand the affine connection. Again, using the definition of the affine connection. If you find any index typo in my calculations, you get an extra point. So you've got to follow closely. I guess not now, at home is easier. So that's 1/2 G rho lambda. Now the affine connection is G lambda tau. I chose as the gamma index, and then we have d mu G sigma tau plus d mu d sigma G tau mu minus d mu d tau G mu sigma. That's of course this guy. And now for the second guy, have to go to the next line. Minus d mu G sigma tau minus d mu d sigma G tau mu plus d mu, d mu, d tau g mu sigma. And now here, it's fine. Oh, sorry. That was the, what did I do? Oh, but now I need to take the derivative of this guy. This was the derivative of everything in the parentheses. So plus 1/2 g rho lambda d mu g lambda tau times d mu g sigma tau plus d sigma g tau mu minus d tau g mu sigma. And then for the second guy, minus 1/2 g rho lambda d mu g lambda tau d mu g sigma tau plus d sigma g tau mu minus d tau g mu sigma. And then the last part we don't touch. So plus g rho lambda gamma lambda mu alpha gamma alpha sigma nu minus gamma lambda mu alpha gamma alpha sigma nu. Ah, lovely, I love these things. Right, but eventually there is nothing really here. I just use the definition of the affine connection, right? The inverse metric times the derivative, the first derivative of the metric, plus and minus, and then I just took the derivative in there. Right, first I took the derivative of everything inside the parentheses, and then I took the derivative of the inverse of the metric, right? Now, okay, what was that good for? So partial derivatives do commute, which means that this guy here cancels with this guy here. So that's good. And so what we left from this guy, again, I have lambda is a dummy index. G rho lambda, G lambda tau. And I have here tau, so I can simply replace it with the rho. What I'm going to get is a 1/2 d mu d sigma g rho mu, right? Just use here tau lambda, and we can just replace it with a rho here. Okay. And then I have here minus d mu, again, tau is replaced with rho, so d rho g mu sigma minus d mu d sigma g rho mu plus d mu d rho g mu sigma. Oh, lovely. Okay, now we have this guy here. This guy here, it's the same color, but it's a different color. Choose this one. So for this guy here, okay, I can use the following trick. I can write G rho lambda d mu G lambda tau as minus G lambda tau d mu G rho lambda, right? Just took the full derivative, which is 0. But now I can expand that. Remember, we had the metric compatibility, so I can write it down as minus G lambda tau gamma eta, which is mu rho g eta lambda plus gamma eta mu lambda g eta rho. I promise you it's going to be ugly, but I promise you it's just an algebra. So don't just go carefully over the indices. And you either find that I cheat you or you find that I'm actually doing everything fine.
Where did you get that from?
Everything is in my head. What do you mean? You can find it in any textbook, really.
No, but is it supposed to be like two different affine connections that have this component in them, or
from the metric compatibility, right? You have remember that the covariant derivative of the metric, capital D, G mu nu is 0, is equal to 0, but capital D of G mu nu is just G, the partial derivative plus the gamma times G plus gamma times G, right? Sorry, minus gamma times G, right? This is equal to 0, so you can just take it from there, right? That's from the metric compatibility. Compatibility. And D is equal to 0. Right? Good. Yeah. So after that, what we do, okay, so I take these two lines. What am I doing here? Oh, no, that's okay. And then, okay. Then I have this following trick. So I replace these guys, right? D mu nu with this guy. But now I can take that, and that. And that is just the affine connection. So I can write down this as minus gamma eta mu rho g eta lambda plus gamma eta mu lambda g eta rho times gamma lambda mu sigma. And then the second guy here will do exactly the same, but this mu will replace with a nu. So plus gamma eta mu rho g eta lambda plus gamma eta mu lambda g eta rho gamma lambda mu sigma. And then I'm just copying the last line. So plus g rho lambda gamma lambda mu alpha gamma alpha sigma mu minus gamma lambda mu alpha gamma alpha sigma mu. Great. Great. Now what? Okay. Now what will happen? Okay, good. Now, so this guy. So this guy here cancels with this guy here. Right. Now we have to switch the eta with a lambda. And lambda with an alpha, right? Lambda goes to alpha, eta goes to lambda. I can always do that because these are dummy indices. And then these two guys will cancel. Yes. And then this guy will cancel with this guy. and these two are still there. So we end up with so R rho sigma mu is I'm left with what's written here and these two terms here. So this is just 1/2 d mu d sigma g rho mu minus d mu d rho g mu sigma minus d mu d sigma g rho mu plus d mu d rho g mu sigma plus g eta lambda and minus lambda eta mu rho lambda sigma mu plus lambda eta mu rho gamma lambda mu sigma. Lovely, lovely. I'm sure you love it. I'm sure you love it, but that's as far as it goes. So after we did all that, why did we do that? Because when I look at it like that, I can immediately see a few properties. So the first is that we have a symmetry under interchange of the pair of indices. And interchange. The first and second pair of indexes. Right? So R rho sigma mu nu is equal to R mu nu rho sigma. Right? If I change rho sigma with a mu nu, nothing happens. Right? This guy, this guy, this guy, this guy, and this guy interchange, nothing happens. Sorry, this one's not. In this guy interchange, in this guy interchange, nothing happens. The second point is that anti-symmetric with respect to a single index exchange. Right. R rho sigma mu nu is minus R sigma rho mu nu, right? Or minus R rho sigma mu nu, or plus R rho sigma mu. So if I switch one pair of indices, I get a minus sign. Switch another one, I get an extra minus sign. Again, follows directly from here. Just look at that. All the properties are just falling straight into your eyes, I hope. And the third is this, what's called cyclicity. There's a cyclic permutation of the last three indices, which is vanish. Right? Cyclic permutation of last three indices, vanish. So R rho sigma mu nu plus R rho mu sigma plus R mu rho mu sigma mu is equal to 0. So again, I told you it's ugly, but it's just algebra. Just have to do it slowly, and you see that that's exactly what it is. Yeah. Okay. So before we're going to explore the consequences of that, I want to introduce some other tensors, which we can introduce even without using the metric. And the first one that I'm going to introduce is called the Ricci tensor. Ricci, actually, it's Italian name. It's called the Ricci tensor. So you write it like Ricci. It's actually an Italian name. So it's Ricci, and is introduced by contracting the first and third indices of the Riemann tensor. So R mu nu is R lambda mu lambda mu. Right? In fact, this is the only independent contraction, except from sine and things of that kind, which we can get from the curvature tensor. Now, the Ricci tensor, from all the properties of the Riemann tensor, it's pretty straightforward to say that the Ricci tensor is actually symmetric. Or properties R mu nu is R mu nu. Okay, that's about that.
Is there a physical meaning to the Ricci tensor?
That we'll wait until next week and we'll discuss it thoroughly. The answer is yes. But so far, what we do, again, I didn't do any physics. In the last few weeks, we're only doing math. Now, this directly follows from the symmetries of the Riemann, and this is something that you can prove at home. Maybe I even ask you to prove it at home, I'm not even sure. If I did not ask you, then just do it, just an exercise. Following the symmetry properties of the Riemann tensor, you can get to that quite straightforward. And if we take another contraction of the Ricci, we get another, what do we get? What do we get if we get another contraction of the Ricci? What type of object do we have?
Scalar.
A scalar, right? That's right. So we get what's called the Ricci scalar. Ricci scalar. So we know that it's R, which is just R mu mu, or Q mu R mu. So the Ricci scalar is just a number. But it's one hell of a number, because to get to that number, right, if we have the metric, we need to get first to the Riemann tensor, and then we need to construct it twice. All right. So, okay. Now let's discuss properties of the Riemann tensor in n dimensions. What we're really up to is to calculate the number of independent components that the Riemann tensor has in n dimensions. So we started with saying, okay, it has an n dimension, it should have n to the power 4 Sorry, yeah. Let's see if I didn't miss anything. No, I don't think so. Okay, we started by saying that it has n to the power 4 independent components. Now, but we know it's anti-symmetric in the first two indices and anti-symmetric in the last two indices and symmetric under interchange of the first two and the second two. Right? So if it's symmetric under interchange of the first and the second two, right? Again, we can think of it as okay, symmetric under interchange. You know, rho sigma and mu. Right, so we can think of it as R rho sigma mu. Right? How many, you know, we can think of this as, you know, each pair providing a set of, you know, individual index, right? Mu and u is an individual index that goes, say, from 1 to m. So how many total independent components have a symmetric m by m matrix? How many?
M times m minus 1 over 2
Plus 1.
plus 1.
We also have the m, right? So we also have the diagonal. And everything above or below the diagonal. So we have an m times m plus 1 over 2 independent component. Right? But we said this each of these m is by itself a matrix, which is anti-symmetric. Right? So each m represents, or each index, right, represents you know, n by n anti-symmetric. Right? Because we have two indices which are anti-symmetric, the first pair and the second pair. Right? So how many independent components does it have? You know the answer. You said it.
N times n minus 1 over 2. That.
All right, so it will have an n times n, so number of independent components would be n times n minus 1 over 2. Right? So totally, we're going to get, so total, we have 1/2 times m, 1/2 n minus 1, times m plus 1, which is 1/2 n minus 1 plus 1. Number of independent components. So if you plug it in, that's 1/8 n to the power 4 minus 2n cubed plus 3n squared minus 2n independent components. So that's less than n to the power 4. Now we still have the cyclicity, which we haven't used. And that means that the total anti-symmetric part of the Riemann tensor has to vanish. Right? R rho sigma mu is equal to 0. That's the You're familiar with this notation, right? I think we discussed it. So how many total constraints do we have? That might require a little bit more repeating over what you learn in how you call it, combinatorics. So for the first one, we have an n option. Then for the second one, has to be n minus 1. For the third, n minus 2. And then for the fourth would be n minus 3. But we cannot switch them. So we have to divide it by 4 factorial, sorry. So that adds additional constraints. So finally, we end up with 1/8 n to the power 4 minus 2n cubed plus 3n squared minus 2n minus 1 over 24 and n minus 1, n minus 2, n minus 3. And that is 1 over 12 n squared times n squared minus 1. And that is the number of independent components that the Riemann tensor really has. This is the total. What? So how many independent components in 4 dimensions does the Riemann tensor has really? Hmm?
20.
20, right? It's a good number, but that's less than 256. How many in 2 dimensions, by the way?
1.
1. Cool, isn't it? Now I'm going to give you a few examples. We're going to discuss that, but before that, there is one more thing. There is one more identity. In addition to all these algebraic identities, there is one differential identity, which is quite important. So we have to go through it as well. And that's called the Bianchi identity. Again, there are several Italians involved in this business. So far we discussed algebraic properties and algebraic identities. Right now we're going to discuss a differential identity. And the differential identity, so this is differential identity. Which goes as follows. I'm going to take the covariant derivative of the Riemann tensor. Yeah, it's a nightmare. But in order to make it slightly less worse than a nightmare, I'm going to evaluate this in a locally inertial coordinate system in which all the gammas vanish. Now, not necessarily their derivatives, but the gammas themselves vanish. So take the covariant derivative of the Riemann, or mu Let's make this mistake. R rho sigma mu mu. And in a locally inertial coordinate system, where gamma lambda mu mu equal to 0, but not their derivatives. So nabla lambda R rho sigma mu mu is just d lambda R rho sigma mu mu, right? It said all the affine connections are 0. And then in the definition of R, also all the affine connections are going to end up 0. So we're left with 1/2 d over the lambda d mu d sigma g rho mu minus d mu d rho g mu sigma minus d mu d sigma g rho mu plus d mu d rho g mu sigma. What is that good for? That is good for, because if I take the sum of the cyclic permutations of the first 3 indices, then I get nabla lambda R rho sigma mu mu plus nabla rho R sigma lambda mu mu plus nabla sigma R lambda rho mu mu is 1/2. Okay, let's just write it down. The lambda d mu d sigma g rho mu minus the lambda d mu d rho g mu sigma minus the lambda d mu d sigma g rho mu. By the way, while you're copying, does anybody want to guess what the outcome is going to be? The lambda d mu d rho g.
0?
Yeah, it's going to be 0. I'm just tricking you by wasting your time of copying all that. It's going to end up to be 0, of course. Plus the rho d. I'm just switching the order, like d mu d lambda g sigma nu minus d rho d mu d sigma g mu lambda minus d rho d mu d lambda g sigma mu plus d rho d mu d sigma g mu lambda plus d sigma d mu d rho d lambda mu minus d sigma d mu d lambda g mu rho minus d sigma d mu d rho g lambda mu plus d sigma d mu d lambda g mu rho. Now comes the best part, right? G rho nu minus G rho nu. We have all the cancels out. G nu sigma, G sigma nu. These guys cancel out. And G rho mu plus G rho mu. This one cancels out. G nu sigma and the minus G nu sigma. So these guys cancel out. And what is that? This guy cancels with this guy. And this guy cancels with this guy. And of course, the outcome is 0. Now, the fun part is that although I chose locally inertial coordinate system, what I wrote down is a tensorial equation, right? It's an equation between tensors. The equation between tensors that is true in one frame is true in any frame, right? So this is generally true.
Can I ask a question?
Yes.
But isn't this basically like the properties that we said before, the cyclic permutations of at least 3 indices vanish?
No, because now I took the derivative. I took three.
It is a different derivative for each one?
Yes.
Okay.
I took 3 different derivatives here. I took the permutation with the derivative. Right. So we can write it down as nabla lambda r rho sigma mu. This is the sign for cyclic permutation here, right? Is equal to 0, and that is called the Bianchi identity. Now, what we can do with the Bianchi identity, actually, it is going to be quite useful. It is going to get a lot of physical interpretation, and see that in 1 or 2 weeks. For now, what I'm going to take the Bianchi identity and I'm going to contract it twice. So if I have 0 equal G mu sigma G mu lambda, and then the Bianchi identity, lambda r rho sigma mu plus nabla rho r sigma lambda mu plus nabla sigma r lambda rho mu. Then, okay, we have here nabla mu, right, the first one, and then nabla mu, or mu and sigma I contracted, and I use the symmetric part of R, or the symmetric part, so I have an nabla mu or rho mu. And then with the second term, I have a minus nabla rho. And here I have R nu and sigma. I can switch it off and then switch them, right, and then contract. And then again, mu and lambda, I raise one index and I contract, so I ended up with the Ricci scalar. And then with the last one, it's a nabla nu R rho mu, which is equal to 0. Or nabla mu or rho mu is 1/2 nabla rho r. Because mu and u are just dummy indexes. Now, this I can write down in a slightly different form by introducing yet another tensor. But this time it has a name, which is called the Einstein Tensor. If I'm introducing that name, that means that we are pretty close to start using that to do physics. So Einstein Tensor is G mu nu is just defined as R mu nu minus 1/2 R G mu nu. And then the twice contracted Bianchi identity is simply nabla mu G mu nu is equal to 0. Now, Einstein tensor is obviously symmetric because of the symmetry of the Ricci tensor, and I'm not going to surprise you by telling you it's actually quite an important tensor and what's going to follow. All right, questions? Promise you today we're going to do a lot of algebra, and I promise you that the outcome is going to be quite important. For the first part, you see I didn't lie. I didn't lie for the second part either, but you can see it, yeah. Questions? Okay, follow that at home again. Do all the math at home. Make sure that I did not miss any of the indices, and you see what I did there. It is straightforward, but lengthy. Okay, let's go back to the Riemann. This is the total number of how many degrees of freedom, independent components, does the Riemann have in one dimension?
0.
0. Right? So that means that, what does it mean? So if I take a one-dimensional curve, right? So we're going to do a few examples now. Number of independent components of a Riemann tensor. One D over 0. I'm taking a curve. It's a one-dimensional curve. It's not a two-dimensional. It's a one-dimensional. So, you know, if I'm an ant, I can go either this way or this way. What does it mean that it has a 0 curvature? That is not curved. There is no way of curving it. Right? From an ant that walks either left or right, it doesn't know that this curve may be embedded in a higher dimensional space. It can just go either right, left, or right. There's no curve involved from the ant's point of view. If we look from the outside, you can say, hey, you know, this is curved, but no, it's not curved. In one dimension, there is no such thing as curve. All right?
That means that all the lines are the same?
Yeah, all the lines are the same. You can always either go left or go right. That's what you can do. What about two-dimensional? How many independent components does the Riemann has in 2 dimensions? How many?
1.
1. That means that a single number is enough to describe the curvature of a two-dimensional space. Right? Normally, which number this will be?
The slope?
No. One of the things we derived.
The Riemann number? Scalar?
The Ricci scalar, right? That will be enough to tell us everything we need to know about the curvature of the two-dimensional space. Right? Okay. Example. A cylinder. It's a cylinder. Right. What's the curvature of a cylinder?
Zero.
Right, I just demonstrated, right? This is a cylinder. But what did I do? I just took a piece of paper, flat space. We just identify this boundary with this boundary. Right. This is flat space. This is still a flat space. Right? Now, okay, now there is a very subtle point here which can be confusing, and you'll find it in your problem set. That's because I want you to be confused. Right. When I say it's flat, it means that I can find a metric in which it looks flat. But of course, I can describe it with a different metric, which it will not look flat. Right? Now, there are some subtle issues here which I won't get into, which gets into the idea that a metric is something which is it's a structure that we put on the manifold. I don't want to get into that because we don't really need it here. But the metric is independent in some sense of the manifold. You don't see it in a cylinder, but what about if I look at the torus? Is it flat?
I don't think you can make it flat because it has a hole.
Really? What if I take scissors and I cut it here? What do I get?
Can you repeat what you said? I didn't hear.
What if I take a scissors and I cut it? What do I get?
You get a cylinder that you connected from both sides, but the fact that you had to cut it means that you changed something about the torus, no? It won't be smooth anymore.
No. Take a piece of paper, identify this with this, and that is that. I got a cylinder. I won't do it because it's not my piece of paper here is not flexible. If it was made out of rubber, I could do it. Right? So we can think of a torus as a square, square region with the opposite sides, which are identified. That's called the S1 cross S1. So again, it's a very tricky thing here. This is something which I'm not sure that I want to get too deep into because then there are subtle issues here. But that's called conformally flat, essentially. You can't get a metric in which it will look flat. But you can get other metrics as well. What about our favorite? The ball. Right? Two sphere.
No, that you cannot project it into 2 dimensions.
I can project it, but I'm always going to miss something. At least one point.
Yes, but if you take a ball and you deflate it or you cut it open and then you try to flatten it out, it's impossible.
Impossible. That's right. So again, you already did it in your homework, right? So if I take a 2 sphere, then the metric would be. Like metric would be ds squared is a squared d theta squared plus sine squared theta d phi squared, right? That'll be kind of the standard metric. A, of course, is the radius of the sphere. Now, again, I think you have derived it when you're supposed to this, right? If we do the full details, you end up that gamma theta phi is minus sine theta cosine theta. Gamma phi theta phi is gamma phi theta is cotangent theta. And then one of the components of the Riemann tensor are theta phi is d theta gamma theta phi minus d phi gamma theta phi plus gamma, 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 theta, theta, and then will be dummy index lambda, so lambda phi, phi, minus gamma, theta, phi, lambda, gamma, lambda, theta, phi. Everything else will be either zeros or connected to that by symmetries. So that's going to be sine squared theta minus cosine squared theta. That will be a 0. That will be a 0, and that will be a minus of a minus sine theta cosine theta times cosine theta. So we end up this being sine squared theta. Now, if you want to lower one index, then we have r theta phi theta phi. It's just g theta lambda r lambda phi theta phi. So this is just g theta theta r theta phi theta phi. This is just a squared sine squared theta. Now I calculated one component, but all other components here would be either 0 or associated with this component by the symmetries that we find, symmetric or anti-symmetric. Now the Ricci tensor, right? So R mu is just G alpha beta, R alpha mu beta mu. So R theta theta is just G phi phi R theta phi phi theta phi theta, which is just going to be 1. R theta phi is R phi theta is just 0. R phi phi is just G theta theta R theta phi theta phi, which is just sine squared theta. And the Ricci scalar R is just G theta theta R theta theta plus G phi phi R phi phi. That's going to be just 2 over a squared. So the Ricci scalar is constant. Right? Every place along the sphere, we call it constant. And that's why we call a sphere to be maximally symmetric. But it's constant and it's always positive. It's absolutely positive. Right? So that the sphere is maximally symmetric. And it's always positive. That means that the sphere, that's why we call a sphere to be positively curved. It's always greater than 0. The sphere is positively curved. Right. Intuitively, what it means is that if you are sitting on a sphere somewhere, it curves in the same, and you look in each direction, it always curves the same regardless of which direction that you're looking at. Right. So if this is the sphere, and you're sitting here, it always curved the same way, whichever direction you're looking at. And that's the meaning of positively curved. Can you imagine what a negatively curved space would look like?
It would go like a ball.
No.
If we're inside the sphere, maybe?
No. Negatively curved means it will curve in different directions. It will curve in different ways. So it looks like a saddle, a cuff, right? It looks something like that. So if you're here, you curve in these directions like that, but you go in that direction to curve the other way, the opposite way. I'm a bad drawer, but hopefully you managed to get the idea. This is a negative curve. It's a saddle. Capture source. Right, again, if you're in a positively curved space, then it will always curve in the same direction, whichever you look. Negatively curved, it will curve in different ways. Opposite direction. Okay, questions about that? So we have to digest the things a little bit. There is something which is a little bit mathematical. It's quite small calculation. It will take a few minutes. I can do it now or I can do it next time. It doesn't really matter for me. It's called the geodesic deviation. It really belongs here, but I don't mind doing it on next meeting on Thursday. Basically, remember we said, okay, that going back to what we spoke about initially, when we discussed the equivalence principle, right? We said that if we have two people in an elevator which are freely falling, I told you that if they try to measure gravity to a zeroth order, they cannot do it, right? Because everything they do will fall directly, the same way. But to a second order, they actually do have a way of measuring the fact that they are falling. What was that? What was the second order effect? Do you remember?
They were falling towards the center of the Earth, therefore the distance between them would turn smaller and smaller.
Exactly, right? So the vectors in which they fall are not exactly parallel to each other, but they are slightly deviant, right? In other words, if I take a point X, that both follow geodesics, right? So, the geodesic equation on the point X mu and the point X mu plus delta X mu, right, are not exactly the same. There is a slight difference, right? And that slight difference depends on what?
Curvature.
On the curvature, of course. So we can now we have the tool to calculate that, and that's called the geodesic deviation, which means that if I'm looking at two geodesics, namely two paths that are infinitesimally close to each other, I can calculate how much they will deviate from each other based on the curvature of space-time. Now you got the idea. There is a slight mathematical manipulation here. It's not long. It took me about 1 page to derive it, but so I think it will take something like 10 minutes. Do you want to do it now or do you want to wait until Thursday? For me, I don't care. The question is whether you can still focus after all this algebra that we're doing today. That's the thing that I'm not sure about.
How tough is it algebraically?
Not tough. It's just some algebra.
Oh, okay.
But everything I said so far was some algebra. So the question of toughness is the eye of the beholder. What do you say, guys? You still can focus for the next 10 minutes? No, okay. I won't stretch it. Let's do it on Thursday. I'll do it. It will take 10 minutes and then we'll proceed on. Any further questions, guys? No. Again, when you look at it backward, you see that what we did today was, again, really algebra. It looks confusing, which it is confusing. I'm not trying to lie to you, but at the end of the day, after you get used to it, it's pretty much straightforward, and it's really, there's nothing, you know, it's like a math. It's just one thing follow the other. It's mainly a properties of a math, so you just have to understand where they come from, and that's it. There's nothing very deep. We don't need any deep insight to follow what we do today. All right. So I'll see you again on Thursday. And have a great rest of the week.
Thank you.
Thank you. Bye-bye.
Goodbye.
Thank you.
Tell you, we're going to have a very exciting lecture in person. All right.